Hi, I'm Geoff Webb. I'm a professor in the Faculty of Information Technology. I'm director of the Centre for Data Science, and I've been doing research in various aspects of machine learning and data mining for a very long period of time.
So how about telling us a little bit about that research history of yours, what you started out with in machine learning and where you've ended up and why?
So I started out working on computers in education, and as part of that developed techniques for assessing what students were able to do, and realised that that was actually machine learning on data about students' behaviour and performance. And so it was much more generic in its applicability than simply the application I'd started out working on. So I moved from the specific application to the more generic body of techniques.
So you've been working more recently on a variety of techniques. Tell us a bit about them.
I've had a long evolution over a series of techniques, but I guess the major current themes can be broadly grouped into two categories. So on the one hand, there's research about classification learning. So given some evidence from data, how should you best classify objects? And that has been very much informed by the insight that as data quantity increases, the type of model that is going to lead to the greatest accuracy is going to differ, and so there is value in having a variety of different types of techniques that best deal with varying quantities of evidence against ability to create very detailed descriptions of the interactions that are evidenced in the data.
Mm-hmm. So they should be sensitive to the quantity of data, but also the quality, presumably.
Certainly the amount of information that can be extracted from data is going to depend on a large number of factors, some of them being the complexity of the interactions that are going on, and some being the precision of the interactions. So there are many things that affect data that get lumped into the broad basket of quality, and it can be outright errors in data. It can also be imprecision, so you might have values rounded off, or that may come from instruments of varying levels of precision, and all of those factors affect the amount of information that each factor gives you about the thing that you might be interested in.
So all of that suggests that choosing a kind of model, a model family, or a model complexity relative to a particular problem depends on a lot of things, on the quantity of data, on what's driving the data, the interactions involved, and so on. It sounds like a very complex process. You can't just do a table lookup and say, for this problem, I use this kind of model. So how do you do it?
Effective data analytics is still very much an art rather than a science. And you're quite correct, there is no table lookup that you can perform. And I would add to the list of factors that you identified another very important one, that's the techniques you apply should also depend on the outcome you're trying to achieve. So the same data can be used. So different people are likely to benefit from different types of models and information extracted from the same data for different purposes. So a marketing person is going to have very different interests out of a set of data about drug trials from a scientist in all probability.
Sure. Okay, so tell us a bit about your history and how you got into data science.
So I guess it was a product of my undergraduate studies. I did an undergraduate degree majoring, so Bachelor of Arts majoring in philosophy and computer science, and realised that the prospects in philosophy weren't as good as the prospects in computer science, so for pragmatic reasons thought I'd continue in computer science, but I was really interested in epistemology and metaphysics and see data, so machine learning, as being a form of applied epistemology and metaphysics. So given some evidence, what should you believe?
So one thing that suggests to me is that there's a kind of fundamental difference, anyway, between explanatory models and predictive models. So what role do the two play in data science?
So it's very easy to see it as a dichotomy, that you either have explanatory models or descriptive models, but I see it more as a continuum. Sometimes the models that you want to use for prediction, you need to also be able to understand. So it's important that they be white box and comprehensible, which is one of the key things about explanatory models. I guess one of the key things which drives the difference between the two goes back to the different purposes that I was alluding to earlier. It depends why you're analysing the data, whether what you should be after is explanatory models. Sometimes you have some data which you think could enhance your understanding of some phenomena, in which case you're essentially after explanatory models, or whether you're after prediction or something in between the two.
Mm-hmm. So tell us a bit about the bias variance trade-off and how that relates to models, model structure, and complexity.
So the bias variance trade-off is, I believe, a very informative way of understanding some of the factors that affect the error of a classifier. And there are many different ways of thinking about this. And one way I find productive to think about the variance is to think, if you have one learner and you have different samples of data, if you were to feed those different samples through the same learner, you would end up with different models. And if you applied those different models to something you want to predict, unless all the predictions are exactly the same, then your expectation about the error you're going to get, you can set bounds on it on the basis of the differences in the predictions that are made. So if the prediction is a binary outcome, true or false, say, and you have three different models formed, and two of them say true and one of them says false, you know they can't all be right. So you know at most two of them can be right, and you know at most, at the very least, one of them must be right. So just by understanding how the models that are formed by a particular learner vary depending on the sampling process that's generating the data, you can form expectations about what the level of error is going to be. And that's a very approximate way of thinking about the variance. And you can then decompose the total error into the variance term, so the expectation as a result of the variation in terms of the models, and either just a bias term, so the bias term turns out to be the error which was introduced by a mismatch between what the learner prefers to put into models as opposed to what the data is telling it, or a number of other analyses add a few other terms. But what I find most informative is just the two, the dual, the bias and the variance. And how is this useful? Well, you can see that that learners that have very high variance for a certain type of data, clearly you have to expect to have a reasonably high level of error. But the variance you should expect is will decrease as the quantities of data increase, because there'll be less effective difference between the samples. So for small quantities of data, learners that have very high variance are very disadvantaged. They have a kind of very, very high initial error before any bias comes into play. Whereas when you have very large quantities of data, the variance term is very small. So what's most important is to decrease the bias term. One of the key elements that drives bias is the capacity of a model to describe a very wide range of different distributions. If the learner can't describe the distribution, then there's no hope that it will. So the greater the capacity to describe a greater range of distributions, the lower the bias is likely to be, but the higher the variance will be, because the greater the variety will be when you have very small amounts of data. So for large quantities of data, one of the things you want is learners that can describe very broad spaces, alternative types of distribution.
So to put it really crudely, as is my want, you could say that models which take a large number of parameters can be fit to a large number of different relationships, dependency relationships. Those show a lot of variance, relatively low bias perhaps compared to simpler models, but they can do a lot better with large data.
So you need to qualify that by some understanding of effective parameters as opposed to actual parameters that are in the model. So it's possible to have models that are over-parameterized, so they have parameters that have no real effect. So that's one point, and also a second one is it's possible to have a very so the number of parameters is not the only element which controls the type of variety of distributions.
So what do you think of the recent efforts and successes in deep learning?
So I see that very much in terms of the bias variance trade-off. So I see what deep learning is doing in learning higher order features is increasing the representational power, and so decreasing the bias of the system while increasing the variance. So my take is that as data quantities have increased, the power of deep neural networks to overcome their high variance and bring the lower bias into play is increased.
Well, so it's a way of amplifying what data are telling us, more or less, or giving good representation to it.
Oh, well, it is giving a more powerful model, which is only going to be useful once you've got sufficient data to be able to settle on a reasonable representation as a result of that.
So what do you think about the future of data science? Is it a good place for a young scientist to get started?
So I think we're actually still at the very beginning of a hugely exciting field. It's still very much an art. There's a lot to be done in terms of systematising it, but even without looking at it as a research field, as purely an area of application, we're still only exploring the edges of what can be done. One of the things which underlies a lot of data analytics, I believe, is that the world is a highly connected place, and things which on the face of it seem totally unrelated to something you're interested in are actually very distantly connected. So kind of like the butterfly flaps its wings in the Amazon basin, according to chaos theory, might affect the weather in Melbourne. If I may say, I wish it'd make it a bit warmer at the moment.
It'll change again in 6 months.
Very distantly, apparently unrelated things can actually provide sometimes incredibly minute amount of evidence about something we're of interest to us. And as we get more and more data, it's more and more possible to tease out what exactly that form of evidence is. And I believe we're going to ever increasingly be able to develop models that predict incredibly surprising things that you would have thought there was no prospect of being able to predict. And there's great applications of that and scary applications of it.
What are some of the great applications?
Great applications. So in science, so for example, area I'm working in is protein biology, and to be able to carry out laboratory experiments, the biologists need to configure things just right in order to be able to create the conditions to get the results, but they don't know how to do that. So currently they just spend sometimes months exploring different ways until finally they hopefully hit the jackpot using these type of data analytics. It's possible to suggest this is likely to work well for this on the basis of factors that the biologist may not have even imagined would be relevant to it.
So some of what you say seems to run a little counter to the history of data science, that actually what's most widely applied are really simple models that are ignoring the long, distant, minor effects, linear regressions and hierarchical regressions and things like that are throwing out 95% of the variables. So what's the role of that compared to big data analytics?
So I wouldn't quite agree with that. So logistic regression is often applied, I believe, when there are a huge number of factors which are considered to be likely to be involved, and it's able to sort of aggregate minute amounts of evidence from sometimes millions of factors. So it's widely used in analysing people's web browsing behaviour, for example, where you might have 100 million websites of the features. Each visit provides just a micro fragment of evidence, and it's only by putting them all together that you can make a reliable prediction. So I think there are techniques like logistic regression, naive Bayes, that do gather very broad ranges of evidence. I think what is lacking is systems that can both do the depth of deep learning and the breadth of something like a linear model.
Right.
Kevin asked you about some of the positive impacts of data science, and did you get onto any of the negative? Are you worried about anything?
I'm extremely concerned about the way in which the ability to make predictions on the basis of very distantly related evidence, in my view, seriously threatens our current notions of privacy. So I believe that there are already organisations that have so much data about us that they have the potential to predict, well, they do already predict things about us that literally we don't know about ourselves. To give an example of that, on the basis of web browsing behaviour, an advertiser, a car manufacturer, for example, may be able to infer quite well that I would be potentially interested in buying a particular model of car, and I might not even know that that model of car exists. So quite literally, I don't know this thing about myself, and they do. And that creates an extraordinary imbalance when they know a huge amount about me. I don't know anything about them. I sometimes literally don't know the things they know about me myself, so I can't guard against what it is.
Presumably
advertising
you're not
is
worried about guarding against car manufacturers.
Yeah, so advertising is relatively innocuous, but when you put that together with the capacity through online experimentation for these online organisations to become more and more effective in the way in which the actions they take influence us to do the things they'd like us to do, often without us having any realisation, A, that they're trying to influence us, or B, possibly even B, that we're doing what they want us to do. As we don't know any limits on what that might be applied to, in the dystopian possibilities are huge. So I'm a reasonably optimistic person. I don't think that the majority of people have evil intent, but I think a lot of people's objective functions aren't exactly the same as mine.
Do you have any opinions about the singularity or machine intelligence reaching human level and shooting off at some stage in the future?
I will be very surprised if there's any machine intelligence that we would recognise as such in my lifetime. I just don't think that the core of intelligence is grounded in the types of things that computers do. I think computers can do amazing things that we can't do very well.
So you think the technology doesn't fit the problem? Is that what you're saying?
Exactly. And I don't know what the correct technology is.